In object co-manipulation, humans can infer the intent of the other person without verbal communication. When a person senses changes in the direction of motion of their partner, he immediately follows their lead, while respecting the constraints and capabilities of both participants. This challenge of seamless collaboration is not always solved for a robot partner and is sometimes not addressed even in human-human interaction. Robots are significantly stronger and can therefore be better assistants if we tackle this challenge. In this work, we focus on human-robot collaboration tasks, with the robot being capable of assisting in both Cartesian and rotational dimensions. For instance, when a human requires rolling a heavy pot, the robot should reduce the torque on the human wrist. We think our work is the first step in creating truly interactive robots in factories and homes. We emphasize the importance of object transport to a goal pose in full 6D in our paper, and conduct experiments in 3D for evaluation. We propose a novel intent estimation method while considering constraints for both participants. Our method uses 30% less force and 40% less torque over time than the state-of-the-art collaboration method. Our methods smoothly switch the robot role between a leader and a follower. As a leader, the robot reduces the effort of the human, being more capable than a human partner. As the follower, the robot will follow the human lead in instances of ambiguity. Human intent estimation is a formidable challenge. Here we seek a representation of intent that is approximately accurate and shows stability guarantees. We begin by modeling the human intent as an autonomous dynamical system directed towards a specific goal pose. DS-based controllers are robust to disturbances, and combined with an impedance controller, can be used to achieve force-level compliance. Additionally, task dynamics depends purely on motion history, without relying on force-torque sensors. However, using only DS to model the intent is not sufficient, since it only follows the specific dynamics of motion and towards a predefined goal or set of goals, highlighted in orange here. In a realistic human-robot collaboration, the goal and the dynamics towards the goal are not known and needs to be estimated. Using particle filters, we use past velocities as observations and use Bayesian update to estimate the probability distribution of the goal pose and dynamics matrix. We use two separate filters to reduce the dimension of the problem, one for Cartesian coordinates and the other for rotational coordinates. We assume the human has a static intention, therefore the particle filters use zero dynamics models. Intuitively, when the confidence of the estimate is high, a low noise is preferred, so the estimated goal and dynamics stays steady. And when confidence is low, a high noise is preferred for fast changes in the estimation. Based on the estimated states and dynamic matrices, the velocities and accelerations are evaluated. Particles are then scored based on the error with respect to the expected velocities and accelerations. We tailor the particle filtering strategy by trimming the remaining particles to also take into account the constraints of both the robot and human. Because human can freely move in the workspace, they inherently adjust their posture and movements based on environmental constraints. Thus, even though simple, human manipulability can be adopted as an indicator of directional preference, capability, and comfort. We capture human posture during collaboration and reshape the noise of the Cartesian DS based on the hand manipulability ellipsoid axes. To address robot capability, we remove goals that are infeasible for the robot based on inverse kinematics. For computational efficiency, we use Kurobo, a GPU-accelerated inverse kinematic solver. Along with the goal pose feasibility, we also want the robot motion to be feasible. To address this, we respect the joint constraints by generating a repulsive potential to act against violations. In addition, for intuitive interaction, perceived safety, and for the robot Jacobian to remain full rank, the robot should be kept in a specific joint configuration. This can be achieved by employing a null space controller for a set of desired joint angles. Furthermore, the robot needs to adapt its roles by proactively minimizing human effort as the leader, while in instances of disagreement with humans smoothly transitioning into a follower role and relinquishing control to the human. We achieve this by adapting both the noise of the filter and the impedance control gains online. Integrating the suggested steps, we devised a game wherein the human is tasked with moving a weighty object toward a designated goal pose, specified by longitudinal, lateral, and roll angles. Upon reaching the goal pose, the task ends, and the team reverts to the center of the workspace for the next goal pose to emerge. Throughout this process, the robot remains unaware of the ground truth goal pose. The plots show the confidence level and the force torque applied by the human. When human and robot motion is in agreement, the confidence level is high, and the robot leads with a high impedance gain, generating the majority of the forces for motion and deceleration. On the other hand, in cases of sudden changes in human force that result in unexpected motion, the impedance gains drops, lowering the confidence level. In this case, the robot follows the human. The simulation on the top right shows the influence in particles distribution. At instances of disagreement, particles move ahead of the robot, leading the robot to follow the estimated goal. Our proposed approach represents a significant step forward in physical human-robot interaction, promising to extend the application of robots in various sectors by ensuring their cooperative interactions with humans are both safe and effective.